so far, what we've done is we've looked at limits that don't have like an exact answer, right? So if you plug something in, you're going to get something called an indeterminate form. And we've talked about 3 indeterminate forms so far. We've talked about 0 over 0, infinity over infinity, and then anything like 0 times infinity, right? So plus or minus infinity doesn't matter. But these are the 3 ones that we've looked at. If it looks like either one of the quotients, so 0 over 0, infinity or infinity, we apply L'Hopital's rule, right? Which just tells us to take the derivative of the top and the derivative of the bottom and then do the limit like normal, okay? Then we got into situations where we have a different type of indeterminate form, like 0 times infinity. And the way we went about that was we changed the question to make it look like these, and then we did L'Hopital's rule again, okay? So that was kind of the idea of what we've been doing so far. All right, so last time we did a really kind of crazy example with a bunch of trig, and I feel like this might be a little bit too hard of an example to give like on a test or quiz, because I feel like it would just take forever. So let's do something that might be a little bit more up our alley, okay? So example 10, okay, we want to find the limit as x goes to 0 of x times the natural log of x squared, okay? Remember, the first thing we do with L'Hopital's rule is we plug in, right? We plug in and see if we actually need to use it. So plugging in, I'm plugging 0 into my function. So I'm going to do 0 times the natural log of 0 squared. Okay. Well, 0 is just 0. What's the natural log of 0? Yeah, it's kind of going to negative infinity. If you don't see that, just graph ln of x in your calculator, and you'll see that the graph kind of looks like this. And as we approach 0, the y values are approaching negative infinity. Okay, so the natural log of 0 is definitely going to negative infinity. What do you think negative infinity squared is going to? Positive infinity. When you square something, it becomes positive, right? So this is probably going to positive infinity, okay? So this limit is a type 0 times infinity. This is an indeterminate form, right? So that means we probably should use L'Hopital's rule on this, okay? Now, Kevin, do you have your notes from last time? Good. Okay. Now we can't use L'Hopital's rule yet because we have to have it look like a fraction first. Any ideas on how to make this look like a fraction? You might want to look at 2 examples, and maybe example 8 might help you out.
One over x.
Perfect, right? The trick that we did with any sort of like x by itself, especially when x is multiplied like by ln of x, which you can't really do much with, we can change x into 1 over x, right? So that's kind of like the main trick that we do with products. Change this into 1 over x. I know it looks funny, okay? So this becomes the limit, forgot to write this down, as x goes to 0 of natural log of, oh my goodness, I cannot speak and talk at the same, speak and write at the same time, oh my goodness, ln of x squared over 1 over x. So all I did here is I just changed the original equation to look like something that looks like a fraction. Okay. All right. Once we're here, we can plug in again and see if we actually can use L'Hopital's rule, right? So whenever we get another limit, just plug in and see what happens. We'll get the natural log, oh my goodness, I cannot write today. Natural log of 0 squared over 1 over 0. Okay. Now, from up top, I did note that the natural log of 0 squared is going to positive infinity. So just kind of look up top to see where that goes. What is 1 over 0 going to? Infinity, right? If we divide by a really small number, that number is going to blow up, right? So we know that 1/0 is going to positive infinity, okay? Now this is an indeterminate form. Remember, it's one of the two main ones that we looked at in the beginning. So this is an indeterminate form, which means that yes, we can apply L'Hopital's rule. We can keep going, okay? All right. So let's try to figure out how we do this, okay? Now, L'Hopital's rule says we need to do the derivative of the top over the derivative of the bottom, right? Now, here we have some functions that look a little funny. Why don't we just write out what the derivative of the top and the derivative of the bottom is, and then we can kind of piece this together, okay? So let's do the derivative of the top, or the natural log of x squared. Okay. Well, what rule do you think I'm going to use to find this derivative? Chain rule. It looks like there's something inside another function. So we definitely have an inside and outside thing going on. What's the inside function? Natural log, right? Natural log goes on the inside of the parentheses. So that's definitely on the inside. And what's on the outside? Yeah, something squared, right? So we got something squared, okay? Remember, chain rule tells us if we want to find the derivative, first we have to do the derivative of the outside first. So what's the derivative of something squared? Something. 2 times something, right? You're close. All right, and then we multiply it by the derivative of the inside. What's the derivative of ln of x? 1/x, perfect. Okay, once I'm done doing that, you can stick the inside back in the box. So this is 2 times the natural log of x times 1/x. Okay, so this derivative is 2 ln of x. They make the L curvy so you can see the difference between an L and a 1/x. That's the derivative of the top. Let's do the derivative of the bottom too, so we just have it. Okay. Remember, whenever you have a fraction you want to find the derivative, sometimes it's easier to just write 1/x as x to the what power? Yeah, -1, good. Okay. And using the power rule, what's the derivative of x to the -1 power? -1, x to the -2, good. All right. You said -1/x squared, but yeah. All right, another way to write this is -1/x squared. All right. Sorry, I was thinking in my head and then I heard you say it and then I said what I was thinking instead of what you said. All right, now we have all the tools that we need to apply L'Hopital's rule. I know what my derivatives are. I know what L'Hopital's rule is. So I'm going to write an equal sign with an LH on top just to tell myself I am using L'Hopital's rule here. I'm still going to have my limit as x goes to 0. Okay, and I'm going to stick the derivative of the top up top, 2 natural log of x over x. I'm going to put the derivative of the bottom on the bottom, -1/x squared. Okay. Now we're here. Is there a way to simplify that fraction into something that looks a little bit better? Yeah, keep, change, flip. We have a fraction over another fraction. So what I'm going to do is I'm going to keep the top fraction the same. So I'm going to keep 2 natural log of x over x. So that's the top. Okay. I'm going to change the division into multiplication. So I'm going to change this. And then you're going to flip the bottom over. So on the bottom, we've got -1/x squared. I'm going to change that into -x squared over 1. Okay, so I just kept, changed, and flipped the fraction. So now I don't have a fraction over another one. Okay, now taking a look at what I have here, it looks like the x squared and the x might cancel out. So let me know if you don't see how we get to this step, because I am skipping a few steps here. We're going to be left with -2x ln of x. Does everyone see how I got there? Is that right? Did I do something wrong?
That's right.
Okay, that is right. All right, good. Sometimes I get scared. All right. Well, it looks a little bit better than what we started with. What we started with had an x times something squared, and now we just have x times ln of x. Let's plug in and see what happens. Okay, so plugging in, we got -2 times 0 times the natural log of 0. We said from before that the natural log of 0 goes to -infinity. So this is really 0 times -infinity. What does that mean we have to do? I think I
Do it again.
do it again, right? We got to do, oh, did you say more work? Yeah, we got to do more work. We got to do it again. Okay. Before we do L'Hopital's rule again, we have to change it into another fraction, right? Any way we can make this a fraction that we can work with? Yeah, right. We do our trick again. When we have an x here, we can make this 1 over x, and it makes it the same fraction. So not doing L'Hopital's rule or anything. I'm just going to change my fraction into -2 natural log of x over 1 over x. Okay, that's kind of like the big trick that we use with products. All right. Plugging in, it looks like, now I'm not going to do this for you, but let me just tell you, if you plug in, you'll get infinity over infinity, actually -infinity over infinity. Okay, but let's just pretend we did that step. Okay. Let's use L'Hopital's rule again. Okay, so LH over an equal sign. We're going to do the limit as x goes to 0. What's the derivative of -2 ln of x? Well, what's the derivative of ln of x? 1 over x. So -2 ln of x has to be -2 over x, right? Okay, so that's the derivative at the top. We actually found the derivative of 1 over x over here. We said it was -1 over x squared. So I'm just going to stick that here, okay, based on what we did up top, okay? And let's keep change flip again. So let's keep the top fraction the same, -2 over x. Let's change the division to multiplication, and then change the division, or sorry, change the bottom to the flip version, -x squared over 1. Okay. Once I'm here, you can simplify again. We have the limit as x goes to 0 of, and tell me if I'm wrong here, I think it's 2x. I think that's right. Okay. All right. Any questions so far? I know we did a lot. Good. Okay. How do I find this limit? Just plug it in, right? We're going to plug in 0 into x, 2 times 0, and that's just 0. Okay, 0 isn't an indeterminate form, it's just 0. So our final answer is 0. All right. Any questions on example 10? All right. Let's flip our page over now and talk about something else that might happen. Okay. So I know that these problems get kind of tough. I promise you on a test or quiz, I'm going to try to keep them as short as possible, so you're not doing this like for, I don't know, 3 hours. But let's do this one. Okay. Now, just a reminder, L'Hopital's rule, we've dealt with indeterminate forms. We've seen 3 so far. We've seen 0 over 0, infinity over infinity, and we've talked about 0 times infinity. So those are the only 3 that we've talked about so far. I'm going to introduce a new one for you. Okay. In this example, we have the limit as x goes to 1. Don't worry about from the right or from the left. This difference of things. Okay. Remember L'Hopital's rule, we always plug in first. We're going to have 1 over the natural log of 1 minus 1 over 1 minus 1. Okay. All right. What's the natural log of 1? 0. Good. So this is 1 over 0 minus 1 over 0. Okay. What's 1 over 0 going to? infinity, right? 1 over 0, that's dividing by a really small number. That's going to be a really big number, okay? So we have infinity minus infinity, okay? Now, when we see this, this is actually another indeterminate form. It's kind of weird thinking about this because you would think infinity minus infinity is 0, right? I'll tell you, if you go to a future math class, there are different sizes of infinity, okay? There's sometimes you can subtract 2 infinities and get a number. Sometimes you subtract 2 infinities, you get a 0. So I'm going to leave it at that, but that's kind of my explanation for you, okay? This is an indeterminate form. And I won't explain too much, but this might not be 0, okay? That's all I'm going to say for that. Okay, and we'll actually see in this example, it doesn't equal 0. It's kind of confusing. All right, Daniel, do you have the notes? I think you do. Okay. All right, well, L'Hopital's rule doesn't say anything subtraction. It only talks about division. So any ideas on how to maybe make this able to use L'Hopital's rule? Good. The derivative wouldn't help us this time because, well, L'Hopital's rule only works when we have one big fraction. So if we find a common denominator, we can make it into a big fraction, right? Okay. What do you think our common denominator is going to be? Good. Let me write that down. So Michael said the common denominator is ln of x times x minus 1. Okay, and usually the common denominator is literally the multiplication of the denominators. Okay, you can't really mess up if you do that. All right, Dave, let me get you your notes real quick. All right, so let's try to make this a big fraction. We have the limit as x goes to 1 from the right. Okay, I want to make both these fractions ln of x times x minus 1. Okay. Okay. What is going to be the numerator of my first fraction? X minus 1, right? Because the only way, well, I had ln of x in the beginning. I multiplied by x minus 1 in the denominator to make the common denominator be the denominator. So whatever I do on the bottom, I also have to do on the top, okay? So I'm going to take my 1 on top and I'm going to multiply it by x minus 1 as well, okay? What does that make the second fraction numerator be? Or I don't know how to say that. What's the numerator of the second fraction? ln x, right? Because to get from here to here, I had to multiply by ln x. If I do it on the bottom, I have to do it on the top, okay? So this becomes ln of x, okay? Does everyone see how I got the common denominator? I think so. All right. Now that I have the denominators matching, I can literally combine the two fractions into x minus 1 minus ln of x over my common denominator, ln of x times x minus 1. Okay. Is everyone good here? Okay, so I just combined this into one big fraction. Alrighty. Well, let's see what we have to do here. Whenever we have a fraction, remember we should plug in first and see if we can use L'Hopital's rule. So let's do that. We're going to plug in. Okay, we're going to plug in 1. Up top, we're going to have 1 minus 1 minus ln of 1. On the bottom, we have ln of 1 times 1 minus 1. Okay, that's a lot of stuff to plug in. Let's see what that equals. Okay, 1 minus 1 is 0. What's ln of 1?
0.
Good. I'm not going to ask it again on the bottom. We have 0 times 1 minus 1 is 0. So it looks like we have 0 over 0. Okay, remember, 0 over 0 is the first indeterminate form that we've ever looked at. We definitely can do some work with this. So we definitely can use L'Hopital's rule. Okay, so let's use L'Hopital's rule. LH. Okay. Gosh, I didn't think about how hard this derivative was going to be, but let's do it. Let me do this in a different color. All right, the limit as x goes to 1 plus, and let me just write a note that I'm using L'Hopital's rule here. Okay. Can someone tell me the derivative of the top function? Good. And I'm going to put the 0 as well. So 1 minus the derivative of 1 is 0 minus 1 over x. Perfect. Okay. What am I going to have to do on the bottom? Product rule, right? We have a product of two functions, which means we have to do what the product rule says. Okay. So I know that my first function is f, my second function is g. Okay. Got to do the first ln of x. Oop, got to do that. Times the derivative of the second. What's the derivative of x minus 1? 1. Good. Plus the second x minus 1 times the derivative of the first. And the derivative of that is 1 over x, right? Okay, so let me just label this real quick. This was f times g prime plus g times f prime. All right. This looks really messy. Let's just try to clean it up and see what happens. Okay. This becomes the limit as x goes to 1 from the right of 1 minus 1 over x. Okay. And on the bottom, we have ln of x plus, I guess, 1 over x minus, nope, that's not right. X times 1 over x is 1 minus 1 over x. Does everyone see how I got here? Okay. The next thing we're going to do is a little bit of a trick. Okay. I don't like seeing 1 over x's in my function. Does anyone know like an easy way to take out the denominator x to make this look a little bit nicer? Doesn't really work unless you have a fraction over a fraction. Okay, I'm going to give you a trick that a lot of mathematicians use, and just know I'm not going to expect you to know how to do this on a test or quiz. Okay, but let me just show you something that you can do. Okay, you can always multiply by 1. Okay, and another way of writing 1 is x over x. Okay, so I can multiply the top by x and the bottom by x, and I still have the same function. Okay, so this is something that mathematicians do a lot. I don't really know why the textbook gave this example specifically, but let's go ahead and do that. Okay, so this is just a silly math trick. You don't have to know how to do this. I won't give this to you on a test or quiz, but let's just keep going. All right, this is the limit as x goes to 1 from the right of 1 minus 1 over x times x, and then the natural log of x plus 1 minus 1 over x times x. Okay, so I just multiplied the x on top. All right, what I'm going to do now is I'm going to FOIL that x over. Okay, so we're going to take this x and I'm going to bring it over to each of these terms. Okay, all right, so we're left with the limit as x goes to 1 from the right. X times 1 is x. 1 over x times x is 1. On the bottom, we have x times the natural log of x minus x, plus x minus 1. Okay. Does everyone see what I did here? Okay, I know this looks weird. This is just a silly math trick that I use to make things look nicer. I won't give you something that you have to do this on the test. Okay, so just bear with me here. Okay. Once we're here, why don't we plug in and see what we have to do? Okay, so plugging in. We have 1 minus 1 over 1 times the natural log of 1 plus 1 minus 1. All right, on top we got 0. 1 times the natural log of 1 is 0. Plus 1 minus 1 is 0. This is another 0 over 0 type limit. What are we doing this time? What do we have to do next? Do L'Hopital's rule again, right? We got to use, oh my gosh, this is getting kind of tiring. I don't know why I gave these hard questions during this class, but you know, let's keep going. We got this. This is good practice. All right, let's do the derivative of the top and the bottom. Okay, what's the derivative of x minus 1? 1, good. So that's the derivative of the top. What do we have to do to find the derivative of x times ln of x? Product rule. Good. So we got our f, we've got our g. We're going to do the first times the derivative of the second, x times 1 over x, plus the second times the derivative of the first, which is 1. And let me just label what I did here. This is f times g prime plus g times f prime. Okay. I'm not done finding the derivative of the bottom though, right? I still need to find the derivative of x minus 1. What's the derivative of x? 1. What's the derivative of negative 1? 0. So we can kind of just ignore that. Okay. I know this is a lot. Any questions so far? All right. Let's keep going. This is the limit as x goes to 1 from the right. Cleaning things up, the x's cancel, so we're left with 1 plus the natural log of x plus 1, right? So cleaning this up even more, this is the limit as x goes to 1 from the right of 1 over 2 plus the natural log of x. Once I'm here, what's my next step? Plug it in, see if it works, right? Before we ever take L'Hopital's rule again, always plug in and see what you can do, okay? So this becomes 1 over 2 plus the natural log of 1. I think I've asked you a billion times, but what's the natural log of 1? 0, good. 2 plus 0, we get a half. That's not a derivative, that's not an indeterminate form. 1/2 is our answer. All right. That was a little much, wasn't it? I'm going to tell you, the subtraction questions get a little bit crazy. There are examples where they don't. I'm probably not going to give you something like this because it's just a lot of work. But we do know what to do when we see indeterminate forms with subtraction, right? All right. Any questions on example 11? All right. That one was kind of hard. I'm sorry for that one. All right, let's go to the next page. Example number, before we do example number 12, let me just tell you kind of what we did here, okay? Indeterminate differences is what we call something when we plug in and we get infinity minus infinity. So whenever we see this, it's an indeterminate difference, okay? The way that we go about it is the same as what happens when we have a product, right? Basically, we turn the subtraction into one big fraction and then we take the derivative, okay? Now, basically the way we do that is by finding a common denominator, okay? There's another way that we can do this, but let's just not worry about that, okay? All right. Example number 13. Here we have trig functions, okay? Let me do this with you. I feel like subtraction is a little bit harder, which is kind of weird, but yeah, let's go through this together, okay? We have trig functions, which are our favorite type of functions, right? What do we do when we see something like this? What's our first step? Plug it in, right? Never do L'Hopital's rule first without plugging in, okay? So let's plug in. We're going to do the tangent of pi over 2 minus secant of pi over 2. Uh-oh. All right. What's tangent of pi over 2?
It's 1 over 0.
Yeah, 1 over 0. It's undefined, right? Yeah, right. Let me just draw the graph of tangent so everyone kind of sees it. Okay. Remember, tangent kind of looks like the disco man that looks a little bit more smushed. And tangent's kind of like smushed between the lines pi over 2 and negative pi over 2, right? That's kind of how tangent is. Okay. Now we're looking at what tangent does as we approach pi over 2 from the left, right? So we're looking at what happens or what the y values go to as we go from the left. And because of that, that's why Michael said we're approaching positive infinity, right? What happened if we approach tangent from the left? Or, I mean, sorry, what if we were approaching from the right? What would tangent equal? Negative infinity, right? So since we're approaching from the left, we do have to pay attention to where we're going from. We are approaching positive infinity from the left. Okay, so this guy here is positive infinity. Okay. Let's think about what secant of pi over 2 is, right? Maybe an easier way to think about this is what's secant related to? What's secant 1 over? Cosine, right? So let's think about cosine. Cosine is a little bit easier to figure out what it equals. What's cosine of pi over 2? 0. So secant of pi over 2 is literally thinking about what 1 over 0 is going to. What's 1 over 0? Undefined or positive infinity, right? So we're looking at an infinity minus infinity type limit. That is an indeterminate form, which means L'Hopital's rule. All right. Now, last time we said the way we go about this is finding a common denominator. Well, there's no denominator here. So what do you think we're going to do? Yeah.
Sine over cosine minus 1 over cosine.
Yeah. Now I did put my hint here. Whenever we deal with trig functions, especially when we're trying to find a common denominator, try moving things into sine and cosine. Sine and cosine are easy. We know how to take their derivatives. Their derivatives are really easy. And they're honestly just easy functions to work with relative to the other trig functions. So why don't we change everything into sines and cosines? Okay. What's tangent in terms of sine and cosine?
Sine over cosine.
Yeah, sine over cosine. And what's secant in terms of sine and cosine?
Oh, 1 over cosine.
Yeah, 1 over cosine, right? So remembering our trig identities, remember we called them the reciprocal identities, but secant is 1 over cosine and tangent is sine over cosine. Any questions so far? All right. Well, looks like our denominators actually match, so we don't need to find a common denominator. We can just subtract the two numerators, and this becomes sine x minus 1 over cosine x. Okay, so we have a big fraction. What's our next step? Not yet. Remember, there's one thing we have to do before we take the derivative. Plug in, right? Now I want us to get into the habit of doing this because sometimes it actually works out. Now, in this case, it doesn't, but let's plug in. Okay, so we're going to do the sine of pi over 2. Yeah.
How can we plug in at figure they're at? It's the same exact thing. We didn't have to like same exactly. It's not gonna work.
I would say L'Hopital's rule, I'm going by the definition of L'Hopital's rule. Now, you do have a point. It is the same function, so you really don't have to, but the definition of L'Hopital's rule does say like when you have infinity over infinity and 0 over 0. So that's why I'm doing it. But yeah, I kind of feel bad for yelling at you for not for saying to skip it. Yeah, let's just plug in because that's the definition of L'Hopital's rule, but I guess technically we don't have to. Let's do it. All right. Sine pi over 2 minus 1 over cosine of pi over 2. Okay. What's the sine of pi over 2? Sine of pi over 2.
1.
I'm doing this part.
It's 1.
Oh, yes. It's 1. Good. And what's the cosine of pi over 2?
0.
Good. So 1 minus 1 is 0 over 0. This is an indeterminate form, and yes, we can use L'Hopital's rule because, well, L'Hopital's rule only works for indeterminate forms that look like that. Okay. So let's keep going. We can do L'Hopital's rule. I'm going to put an equal sign with the LH on top to mention that we're doing this. Okay. We're doing the limit as x goes to pi over 2. What's the derivative of sine x minus 1? Cosine of x. What's the derivative of cosine of x? Negative sine of x, good. All right, so we're now here. Okay, once we're here, let's plug in and see if we can actually just solve what this is, right? If it gives us a number, then we don't have to do anything else. Okay, so we have to do cosine of x. So cosine of pi over 2 over negative sine of pi over 2. All right, I feel bad for already quizzing you. So we already said that cosine of pi over 2 is 0. We already said that sine of pi over 2 is 1. So this is negative 0 over 1. Is that an indeterminate form?
No.
No, it's just 0, right? So we don't actually have to do anything else because, well, the answer is 0. All right. Any questions on example number 13? All right. Now, I'm going to tell you, I think I even put this on the study guide. I'm not going to give you subtraction on the test. Okay, you know how to do it, but if you're studying for the exam, I feel like some of these get a little bit complicated. So I'll give you a treat and say we're not doing subtraction on the exam. All right, let's go to example number 14, our final type of indeterminate form. These ones are the tricky ones. Okay, so if you thought we were done here, it gets a little bit more complicated. Okay, let's just review. So far, we've done indeterminate forms that look like this: 0 over 0, infinity over infinity. We did 0 times infinity, and then we finally got to infinity minus infinity, right? Remember, L'Hopital's rule only works for like these specific types of indeterminate forms. And if you get these types, you make it into 0 over 0, infinity or infinity, right? That's kind of what we did, okay? Let's see what happens when we have powers. We haven't talked about powers yet, okay? We have the limit as x goes to 0 of 1 plus sine of x to the cotangent of x, okay? Let's plug in first, see what happens. So plugging in, we have 1 plus sine of 0 to the cotangent of 0. All right. Sine of 0 is, well, what is sine of 0? 0, good. So this is 1 plus 0. What's cotangent of 0? It's undefined. Cotangent is 1 over tangent, right? What's tangent of 0?
1 over 0.
Yeah, so tangent of 0 is 0, so this is 1 over 0. Where's this going to? Infinity. Good. Okay, so we are doing 1 plus 0 to the infinity. This is 1 to the power of infinity. Now you might be thinking, isn't 1 to the power of infinity 1? The answer is, why don't you take some more math classes and you'll see that it's not. Okay, so 1 to a power of infinity is not just 1. You can't say that. This is an example of another indeterminate form. Okay, and there's actually 3 types of indeterminate forms that deal with powers. Okay, I'll tell you what they are right up. Okay, 0 to the 0th power is an indeterminate form. Infinity to the 0th power is another indeterminate form. So any 0 power is an indeterminate form, except if it's like an actual number. Okay, and 1 to the power of infinity. Okay, so we got 3 more indeterminate forms to think about that are kind of hard to conceptualize, like what they are. But these 3 are examples of things that you will have to use L'Hopital's rule for.
Why is it not 1 or why is it not 1? Because 1 times 1 times 1 times 1 times 1 times 1 to the power of 1.
It does. It seems like it should be 1. I'm going to tell you it's not. That's basically the answer. It's this one. So I will tell you the answer. Well, I can't tell you a real number because this is going to be a real number. So even though this limit is 1 to the infinity, I'm going to tell you the answer. The answer is e to the 4th. So the answer to this limit is e to the. I know it's weird. 1 to infinity. It seems like the answer should be 1. This is actually going to e to the 4th power. Okay. We'll see why. Okay, but just know that when you see 1 to a power infinity, I know it's so tempting to just write 1. Even when I'm looking at it right now, I just want to say that the answer is 1. The answer is really e to the 4th power. Okay.
E to the fourth is one, but where does that?
All right. Well,
Where does one translate to E?
we'll see how that happens. We'll see. Let's just make a new branch of math where e to the 4th power is equal to 1. Then we don't have to think about it. All right. I'll tell you how to start it. I don't think we'll have enough time to finish it, but we'll see what happens here. Okay. Now I can't use L'Hopital's rule here because I don't have a 0 over 0 or infinity. That's not there yet, right? We have to change this into some sort of fraction, right? Now it's very hard to see how a power turns into a fraction. And let me give you a hint as to what we're going to do with this. Okay. Why don't I just make the inside equal to y? Okay, so let's just let y equal 1 plus sine of x to the cotangent of x. Okay, so essentially we want to find the limit as x goes to 0 of y, right? Does that kind of make sense? Okay, so I'm just replacing the inside with y. Okay. Now, does anyone remember how to make a exponent kind of not an exponent? I don't know if that makes sense. All right, I'm going to do something weird. Why don't we do this? I'm going to take the natural log of both sides. Okay, so the natural log of y. Oh my goodness, I can't type. Or, right? The natural log of y is the natural log of 1 plus sine of x to the cotangent of x. All right. Anyone remember any tricks we can do here?
One over ln of y.
That can work, but it won't help us. Anyone remember taking calc readiness and something to do with properties of natural log? You remember any properties of natural log we can do?
Oh, wait, can you multiply cotangent times ln of all that?
Good. I know it looks funky, okay, and maybe if we had simpler numbers, it would kind of jump at you. Whenever we have a natural log and an exponent, okay, we can take the exponent and we can move it in front of the natural log. Okay, so we're actually going to use a property of exponent here. Okay, and I know it sounds confusing. In the future, we're going to kind of make this more systematic so you'll know what to do. You're not going to have to be too creative here. Okay, but this turns into the natural log of y equals cotangent of x times the natural log of 1 plus sine of x. Does everyone see how I got from this step to the next? Okay, so we just use, let me just write out properties of logs. Okay, now in the future, what we'll do is this is a very systematic process. Anytime you see something with a power, you're going to do the same thing. Okay, but I think on Wednesday we'll talk a little bit more about this, and I promise you it's not that bad. Okay, I know it looks bad right now. It'll get better. All right, I'll see you on Wednesday. I hope you have a great rest of your day. I'm sorry for giving you kind of harder problems today. The exam won't be like this, I promise. And I'll see you Wednesday.